Alright, in this video I'm going to do a pre-lab lecture on the experiment entitled Separation of a Mixture. And so the first thing that I want to discuss is the difference between heterogeneous and homogeneous mixtures. So a homogeneous mixture is one that's like salt water. Salt stays salt, water stays water, and when you mix them together, it is not obvious to the eye. That there's more than one thing there. On the other hand, there is heterogeneous mixtures. Heterogeneous mixtures are kind of like sandy water. Sandy water, you can tell there's sand in there, that you can tell there's water in there. So it is obvious that there's more than one thing in that mixture. Both of these kinds of mixtures can be separated via physical means. Another thing that I want to discuss, which is very frequently confused, is what the difference is between extraction and decantation. Okay, so extraction is something that's really a precise term, and extraction is frequently only used when you are separating two liquids from each other. So usually extraction is liquid-liquid. That's when you use that thing that's called a separatory funnel. Okay, in a separatory funnel, you can see that there are two layers of liquid, and you drain off the lower liquid, which allows you to separate them. You can't use extraction as a technique when you have a solid from a liquid. So a lot of times I get students saying that they're going to use extraction to get a solid away from a liquid. It's really not what you're doing. When you're doing that, what you're doing is you're doing a solubility, or you're dissolving one kind of substance in the solvent, and then you're doing a decantation. Decantation is what you do to separate a liquid from a solid. Okay, so extraction is when you have two liquids that you're separating from each other. When you want to get something that is dissolved in a solvent off of a solid, that's when you use the process of decantation. Okay, now the next thing I want to discuss is this percent weight. So percent weight is, again, like all of these percentages that I've talked about, it's just kind of the same thing as giving yourself a grade on an exam. The percent weight of a mixture is the mass, or weight, again for me mass and weight are synonymous, the mass of whatever kind of compound you're discussing, generally in grams, divided by the total mass of the mixture, also in grams, times 100 to get it as a percent. Now the thing about this is that you can use it as a conversion factor. So I'm going to make some stuff up right now. Let's say that you have a mixture that is, I don't know, let's do 15% compound A, 30% compound B, and the rest of that, 15 and 30 is 45, 100 minus 45 is 55, 55% compound C. Okay, so we have this mixture, and it has these different percentages of each one of these components in it. So it's a 3-component mixture, and we want to know if we have 5 grams total of the mixture, how many grams of each component do we have? Okay, so you have 5 total grams of this mixture of A, B, and C, and we want to know of that total 5 grams, how many grams of A, how many grams of B, how many grams of C. I'm to tell you, because it's me, and you guys should know this by now, we're going to use these as a conversion factor. These percentages really are conversion factors. All right, so I'm going to do A in this blue color here. Let me switch to a blue color that matches. 15% A means that there's 15 grams of A in every 100 grams of the mixture. That's a conversion factor. And again, like this is exactly the same thing like on an exam. Like if you took, you know, an exam that had 50 points and you got 25 right, that means you got 50%. That means if there were 100, you would have gotten 50 right. 50 out of 100 is the same as 25 out of 50. So a percentage can be used as a conversion factor. So since we now know that 15 grams of A is in a 100 gram mixture, now it becomes very straightforward dimensional analysis. We have 5 grams of the total mixture, so we're going to start there. So if we have 5 grams of the mixture, we know that every 100 grams of the mixture contains 15 grams of A. So 5 times 15 divided by 100 gives us 0.75. And we can keep doing that. So B, let me switch colors here. I'll do this nice pinkish color. We have 30% of the total mixture is B. So that means we start with 5 grams of the mixture. We know for every 100 grams of the mixture, 30 of those grams are component B. 5 times 30 divided by 100 means that you have 1.5 grams of the mixture is B. Now C obviously you can get to by taking 5 grams minus 1.5 grams of B minus 0.75 grams of A. But this is how you can determine the how much of each component makes up a mixture given the percentages. And again, I think this is an easy way of doing it. If you want to do it a different way, I don't care. But the key is that you understand exactly what you're doing, how you can get the mixtures ratio of things from the percentages. Okay, now let's actually talk about the Prelab. Okay, so I get a lot of heat from this, people saying that the Prelab is really hard. Let me walk you through and tell you how it's not so hard. 2 substances are given to you that need to be separated. So compound A is soluble in water. So that means it dissolves completely in water, and it is insoluble in hexane. That means it doesn't dissolve in hexane. Compound B, on the other hand, is the reverse. Insoluble in water, soluble in hexane. And these are both solids. Maybe that's where the confusion is lying. Maybe I need to be really explicit that A and B are both solids. You really don't talk about solubility of things unless you're talking about solids. So here A is a solid that is soluble in water and insoluble in hexane. B is a solid that is insoluble in water and soluble in hexane. And our goal at the end of this, well, I do say your end result is to have solid A separated from solid B. Okay, so let's mix these two things together. You have A and B together in a flask, and they're two solids and you can't tell the difference between them. It's not like you can go through and filter them. They're not different shapes. So what are we going to do using this solubility to separate A from B? There are 2 possible routes. The first possible route, let's see what happens. And I'm going to just move this over real quick because I decided I was going to do 2 routes. I'm going to move this over to here. All right. Let's say, oh, okay, go away. There we go. let's say we take this mixture of A and B and we add water to it. So we add water, we stir it, we make sure we give it some time. What happens to both components when you put water in it? Well, since A is soluble in water, the A dissolves into water, right? I mean, that makes sense. Think about if, again, you had something common that's soluble in water like salt. If you put salt into water, stirred it up a little bit, it would dissolve. And then B, since it's insoluble in water, stays a solid. Okay, so now in your flask or beaker or Erlenmeyer or whatever, you have some liquid in there. It's not water anymore, it's really a solution of something. And you have some solid in the bottom. So what's going on in that liquid layer is you have A dissolved in water. And, oh, that should be in purple, my apologies. All right, I'll color this in purple up here. This is purple liquid. And down here, you have B that, since it's not soluble, stays a solid. You can separate those two things via decantation or filtration. You just pour the liquid part of A that's dissolved in water off. So to one side, you have A dissolved in water, and over here you have B that's a little bit wet with water, right? Because, I mean, after you decant off the liquid A that has water and A in it, you still have some wet B. Okay, so now we've actually done our separation. We have A in one beaker, right? Over here we have A as a liquid. You know, A is dissolved in water. Over here we have our beaker that just has solid wet B in it. Again, the goal is to get solid A separated from solid B. So what do we have to do to A that's dissolved in water to get solid A? All you have to do is heat it. If you heat it enough, you'll eventually get the water to boil. As the water boils away, you're left with solid A at the bottom of the beaker. Now, what do we have to do with B to get it completely dry? Once again, all you have to do is heat it. That means that you'll get solid B at the bottom. And over here we have solid A at the bottom. Okay? I think that these flowcharts are an amazing way to keep things straight in your head insofar as what's really happening during separation of these things. Now, on the other hand, like I told you, there's actually another way that you could do this if you wanted to. You again have A and B in a beaker together, solid A and solid B. Rather than starting with water, let's think through what would happen if instead of adding water, we added hexane. Well, we know that A is insoluble in hexane, so that's going to stay a solid. It does not dissolve. We know that B is soluble in hexane. So what happens is you get B that is dissolved in hexane as a liquid layer. You get solid A as a solid. You can decant the dissolved B away from solid A. And then again, in order to drive the solute off, the solvent off, you just heat it to boiling. You get solid B separated from solid A. And that's all there is. So you heat it until it boils to evaporate it away. And this, again, this process is using solubility in order to then dissolve a substance selectively. We're selectively dissolving a substance and then decanting it away from the other one. Now, for your particular experiment, it's a little bit trickier because it's a 3-component mixture. You have chemical X, naphthalene, and sand. And your goal, the goal of this experiment, is to get sand. Does not have to be dry, okay? It can be wet or, have any other solvent in it. It doesn't matter, but we're just going to leave sand. It doesn't have to be dry. You're going to stay with dissolved naphthalene. So again, we're not trying to get that dry. The naphthalene is going to stay dissolved. But the biggest thing that you're trying to get to is dry chemical X. And you can definitely read through the lab. The whole point is that chemical X is a compound that needs to get back to the group that synthesized it. And so it needs to get back there dry. And so this is the goal. To get dry chemical X in as few steps and using as little compounds as we need to in order to do the separation. So in order to sort of help you through that, you have part 1. We're going to determine solubility of those compounds. From the solubility of those compounds, we're going to sort of come up with some idea of how we can do the separation. In part 2, we are going to quantify the solubility. I'm going to be asking you why you think we need to quantify the solubility when we get to lab. And then part 3, we are going to test the separation scheme to see how well we did. And in order to test the separation scheme, you're going to get 5 grams of the mixture. That is 20% sand, 70% chemical X, and 10% naphthalene. All right, so in lab, again, I'm going to be your hands. You're going to be talking to things with your neighbor to figure out the solubility of these compounds in 3 solvents. You're going to quantify that solubility. And again, this is the biggest question that I'm going to be asking. Why are we doing that? What's the point of that? What do we get from that? How do we use that quantification in order to go forward to make the most efficient scheme that we can? And then in part 3, we're going to test our separation scheme. All right, I think that's a pretty decent pre-lab, more than I usually give. So I hope that helps you with the pre-lab and coming to lab prepared. As always, if there are any questions, let me know.